Well, good morning, folks. How was lab? Nobody lost an eardrum or anything from the large squawking sounds, or yeah. And any leftover questions from lab 3 at this point? I put up a waypoint for lab 4, and by next Thursday I'd like you to have one complex iterator pipeline running in simulation. This is the last weekend to work on lab 4 before it's due. Yikes. Now, unless of course you don't spend all of spring break someplace else, but so have you started thinking about lab 4 yet? Zzz, yeah, I know. I'd be happy to talk more about lab 4, about iterator pipeline. I think the pipeline is relatively simple compared to the last system you were building. And should be fairly straightforward to simulate, because you only need to test a couple of input conditions for the waypoint, and the output should be a single number rather than a waveform. And the single number you're going to put out is for one point inside Mandelbrot set and 1 point outside the Mandelbrot set, and preferably a little ways from the boundary. Make the iterations of your simulated pipe be the same as MATLAB produces. Then you can be pretty sure that the pipe is working correctly. So you probably want to be out in a region where the system diverges in 2 or 3 iterations, and then inside where it doesn't diverge at all. And so your simulation should run for 1,000 complex iterations, and then halt, because you're not letting it run past 1,000. But for testing, you could make the cutoff be 100. It doesn't have to run all the way to 1,000. It just has to stop. So you might set the max n equal to 100 for testing, rather than 1,000. I decided I should spend a little more time playing with memory. So I wrote there it is. So I wrote a couple of examples, and the example I finished, I don't know, 20 minutes ago, so it's still fresh in my mind, is to take a SRAM that's connected to the Qsys bus. There's a Qsys defined SRAM module which has one port going up to the HPS and the other port exported to the FPGA. There's 2 slave ports on the dual port RAM. So slave 1 goes up to the HPS and slave 2 is exported to the FPGA. Now this is interesting because it gives you a slave that can be written from either point, and therefore it looks like a scratchpad memory from both sides. So it's a communication port with memory between the two sides. You have to worry about synchronization and various other things, but it's pretty handy for getting parameters in and out of the FPGA, because you can write at full bus speed from the HPS into the SRAM, and then those values are persistent there and can be read arbitrarily by the FPGA without having to write a bus master, because you can just manipulate the slave port directly. So what I did then was on the FPGA side, was to instantiate an M10K block. So read two numbers out of here, first number, second number, do a floating point add on those, an F add, store it into the M10K block, and then write the M10K block back over to the SRAM. So that exercises reading and writing. Let's make it like this. This exercise is reading and writing from the Qsys RAM, which is actually M10K blocks, from an explicitly inferred M10K block. And then on the side, I made a MLab counter. You read out of MLab, you add 1, and you write it back into the MLab block. So it's a memory-based counter. And this was just to make sure I understood how the MLab works. And it turns out the inference model for MLab blocks is exactly the same as M10K blocks. They have the same delay structure. They have the same read and write requirements. You can use the same Verilog code to infer one or the other, depending on how you set up the parameters. So this then exercised all the memory kinds I know of on the chip except registers, and I think everybody knows how to do that already. So the memory page gives some idea of what memories are available. I copied out the Verilog simple dual port code, which is just about the minimum you could imagine for a memory block. If the write enable is high, write it, and always read it. This particular version has a split clock, but you don't have to split the clock. It has a read clock and a write clock separately, but you don't have to split the clock. So I also included some of Mohammed's code, which talks about how to simulate that same module with the appropriate pipeline so that it simulates correctly. But the fun stuff was to modify Qsys so that one of the ports was attached to the FPGA. Qsys has this, I can't call it a feature. I'm not sure it's a bug. If you click and remove if you add a connection to a module that has an exported variable, it deletes the name of the exported variable and does not restore it when you unclick the connection. It is therefore simply gone. I've done that a bunch of times because as I'm scrolling through, my click finger happens to hit the button and blows a connection out. So be careful of that. But the overall setup is that there's a clock, and which is set to 50 megahertz using a clock bridge. And port 2, S2, slave 2, is being run off of the HPS heavyweight bus, full width bus. But slave 1 is exported to on-chip SRAM S1. So the signal group is exported, and after you compile and look at the instantiation block, you see something that looks like this. There's lots of signals that come out. There's an address, a clock enable, a chip select, a write, read data, write data, and byte enable. So the clock enable with chip select, you can just lock high and connect the state machine to this side. So an address, a write command, read data and write data. And I wrote out an MLab block here, which it turns out is exactly the same as the M10K block. And the state machine for doing this is extremely straightforward. You connect up the MLab block with no difference between it and M10K block. Then the memory-based counter is just 4 states. Set up an address, wait one cycle for a total of 2 cycles, 1 cycle, 2 cycles, do the read to get the data out, and then do a write to write it back in plus with the data buffer +1. So the state machine works exactly like the documentation suggests. You set up a read address, you wait, you pause an extra cycle, you read back the data, you write the data, done. Yeah, where am I? So the interesting thing was to get this loop going, because it took a lot of states. It actually took about 20 states to get all this stuff going, because you have to do a read, a wait, a read setup, a wait, a read, a write. It took two states to do the add once the numbers were in position, because there's a 2-state pipeline in the adder, in the floating point adder. But when you finally get everything right, you can see that the partition merge RAM summary table from the compiler says that, yep, there was a block called M10K256 and MLab 2032, which are the names I gave the modules. So it actually instantiated them. And this was interesting to check, because the first time I wrote the code, I made a typo in the write data name for the M10K block. And the compiler rightly said, this fool never wrote to the block, we don't need it, whoosh, and left it out. And so my first notice that something was wrong with my code was the M10K block wasn't in this list. So if you've inferred an M10K block, make sure it's there, because otherwise it's been optimized away, probably because of a mistake. The other thing is that this M10K block I specified as a 32-bit by 256 word, as you might be able to guess from the name here, was actually instantiated as a 4 by 27 because I was only writing 27 bits and I only wrote 4 words. So the clever compiler optimized away some of the memory. Now, in fact, it has to use at least one block. So it built the whole block, but it correctly deduced that those were the only memory addresses I was using with this many bits each. Once I saw that error message, then I went back to the message list the compiler puts out in the flow summary message list and typed in the word infer, and sure enough, it wasn't inferring the RAM, so I typed in implicit and I had mistyped, and that gave me the mistyped word. So I put in the extra underscore and then it worked. But that's always worth checking. Now, because the HPS is involved, there's a program running on the HPS that allows you to interactively input a float parameter 0, a float parameter 1, and an address. And what the code does is to take the first float parameter and write it into this address, RAM address, in this dual-ported Qsys SRAM. So I also should say that what I did to write this back was I put this in address 3, and then that was copied into address 3 of the Qsys RAM. So I printed out 8 slots of the memory. 8 slots of the memory. Address 0, address 1, I typed in a 5. Address 3, address 2, I typed in a 3. Then I gave it the command 110, which writes a 1 into position 0. Position 0 is the handshake. If the FPGA sees a 1 in position 0, it says, new data. Executes the sum, does the store and retrieve and store, clears the flag, and that all happens before the first print statement occurs. And so address 0 is always 0 because it's been cleared by the FPGA before the first character comes out of the UART. So on the HPS side, this little program is running, and sure enough, address 3 has an 8, which is 5 plus 3. That's good news. So the code is the usual straightforward but tedious code, which you never know for sure that you understand until you actually do it, which is why I did it. This first piece is testing the floating point modules, and you probably don't need to know that now. But then I wrote this combined SRAM M10K state machine that, in fact, checks SRAM address 0, reads SRAM address 1 and 2, does the floating add, writes sum into M10K block address 3, reads it right back out again, boring, reads it right back out again, and dumps it into SRAM address 3, and then clears the flag. And the only way I've been able to figure out to keep all this stuff straight is to make very obviously different control blocks for each of the memories. And where I messed myself up this time is I put underscores in these but not in those, and I mixed them up. Bad style. I'll fix that. But I ran out of time today. So there's a read data line, which is a wire because it's being driven by a register in memory. There's data buffers, which is just a data buffer I'm using for general computation, a write data, read address, write address, and a write command. And then you instantiate the M10K block. The most obvious fashion, connecting up the data lines and the clock line and the read and write address line. Then we had to instantiate I had to instantiate a floating point adder, so there's a couple of arguments. Takes a clock, the two arguments as inputs, puts out a result, and I marked these memory 1, memory 2, and memory 3 so I could remember where they were going. And then we merely plod through the state machine, setting up an SRAM address 0 to find out if there's new data, waiting a cycle, and then reading the address 0, and then asking in the next state, is there new data? If address 0 equals 0, we just bounce back to state 0 and try again. Otherwise, if it's non-zero, actually do the add, go on to state 4. And I tried to break down the logical stanzas by using dashes in the comments. So the dash comments until the next dash comment is one logical operation, which is to read the first Qsys SRAM number. So we set up the address, we wait a state, we read the argument, the floating argument. So those three read the first argument. Three more states to read the second argument. Set up the SRAM address to 2, wait, read back the data into argument 2. 2 cycles after that, the floating point sum is available. Again, I ran out of time and I had an error, and so I put an extra wait state in here, but I don't think you need that second wait state for the add. Then we write to M10K by using the M10K write address to 3. We put in the floating point result there. We wait. We don't wait because it turns out it's not necessary. You read from the M10K block, wait 1 cycle, just like you do for MLab or any other on-chip read. Read back the M10K data into the data buffer. Set up the write. Set up the write back to the SRAM. And then clear the flag. So this is the address 0 flag. We're going to write 32 bits of 0 to it. And that tells the HPS that the FPGA operation is complete and it can carry on. So it's straightforward. It is merely tedious. But the discipline is set up a read, wait 1 cycle, do the read. Set up a write, immediately go ahead. The MLab state machine is more straightforward, smaller. I think I already put it up. We define the MLab block and do a 4-state state machine, and it's done. Down here, after the interface block, there's the M10K block. It's M10K 25632. It's 32 bits, 256 words, and I forced it to no read write check M10K. No read write check says I'm never going to read and write the same address on the same cycle, so I don't care what you do. That allows the synthesizer to be more flexible. And M10K says, put it there. You don't have to put that in. It'll do the right thing most of the time. But for testing purposes, I wanted to put that in. Then the MLab module is virtually the same code, except the synthesis RAM style is set to MLab. So the rest of these modules are all the floating point stuff. It goes on for pages and pages. So manipulating memory seems to follow the documentation just fine. It seems to work the way the manual says it works. These are all full speed reads and writes, so I don't think I was taking any shortcuts. The only possible shortcut is that the other port, well, no, I don't think it is. The other port of this port's running at 100 megahertz, this one's running at 50. So depending on exactly how the core works here, maybe I didn't have to put a wait cycle in. I'm not sure. But it's a safe thing to do. Put in a wait cycle after you write right. So for Lab 4, you might think that this would be one way of communicating rendering parameters for the Mandelbrot set from the HPS into your compute core. Say the corners of the rendering region, the complex corners of the space you want to render, or more detailed information than that. Color map, whatever you need. These memories can be pretty big. This memory, I think you could probably make this memory 200 blocks of M10K blocks if you wanted. I only use one, but you can make it rather big. If you make the memory bigger than one block, then Qsys takes care of the addressing so that it just works. If you were to specify here 32 bits by 256 words just fills one M10K block. If I'd made this 1024 words, it would have used 4 M10K blocks and generated the necessary address circuitry to hide that from you. So you just give it then a 10-bit address, and data would come back out of the array of 4 M10K blocks, and you don't have to know there's 4 blocks. So the output multiplexers and the addressing are generated for you automatically to concatenate memory blocks into larger arrays. So the question occurs, could you actually render the Mandelbrot set into M10K blocks? You need 302,000 bits. There's 4,400 on-chip memory bits. So there's enough memory to render a binary Mandelbrot set into on-chip RAM and display it directly from on-chip RAM. Dual-ported RAM to the VGA core. Now, only 2 levels, right? You have black and white, green and red, whatever it is. And So you may find that you don't want to do that, but you could. You're probably going to render it into SDRAM or into whatever default RAM is running the VGA controller that you're using. This version of the code, by the way, this version of the code that handles the memory not only has floating point in it, it has a modified video controller that uses only SDRAM. And I did that because sooner or later this is going to grow into some sort of graphics application. But the modified controller that uses only SDRAM and no on-chip memory is in this code if you want to use that instead of the default memory setup for VGA. So yeah, do you have any memory questions? Did you see any obscure stuff? Yeah?
Is the video controller with just the SDRAM slower to write to? On average, yes. Now, if you're only writing to it from the HPS, you cannot write fast enough to cause a problem. So you can write 5 million pixels a second from the HPS and not cause a video artifact. If you write at full bus speed from the FPGA side, I don't know for sure, but I'll bet you can override it. I bet you can overrun the average, and then the SDRAM will fail, and the image will tear to bits. That's one reason I said that if while you're rendering, the image is ripped up because the sync is being destroyed by your writing operations, it's okay for this lab. So if there's a video artifact while you're computing, but that allows you to compute faster, go for it. But that is a potential problem. If you use dual-ported S-static RAM, you don't have that problem, because the VGA controller gets one port, your code gets the other port. So realistically, how many people are going to be here next Friday? 2, 3, 4. I think what's going to happen is Mohammed is staying here for break, I believe, and I expect to see him here this morning, but he's not. So he will probably be doing the lecture next Friday will be in lab under Mohammed, because I have to go off to the airport. What about next week in general? Given the short time frame here, would you prefer to have more lab time and less lecture time? Yeah? All right. So Wednesday, Monday and Wednesday, the whole disaster? Yes? Was that a
I feel like we should have
one lecture on Monday?
Maybe Wednesday for some last minute Q&A before.
I see. Okay, but I can also do question and answer in lab, right? Because it's not like I'm going to say no. So is the sense of the group then all lab time next week? Okay, that's easy. Sure. Final projects.
There's no final project proposal required for this course. I just assume you're going to come in the day after Lab 4 finishes and be ready to go with it. All right, that's the deal, right? You have 4 weeks to finish. It starts as soon as Lab 4 ends. And so 2 weeks from now, more or less, need to have a good idea of what you're going to build. So what do you think you're going to build? Who's got some ideas? And we haven't talked about video input at all, but I have some examples up. You can grab video at full video rate, which means you can do image analysis. Yeah.
Oh, something I was hoping to do, but I'm not really sure how feasible it is. I was hoping to do like word recognition.
Which kind of recognition?
Word recognition. If you held up like something with a word on it,
Duck.
a sign or something, it would
Yeah.
recognize it. And be like,
So I think that that's possible. There's enough CPU on here to do that. I think that there's some software packages that would probably help. Some of the OpenCV stuff probably has some OCR stuff that would help. I don't have a good feel for how it interfaces between the FPGA and the HPS. Clearly there'd be some FPGA because that's where the video connection is. And probably some HPS if it's actually using OpenCV. So, and I don't know how beastly it is to port OpenCV to a new Linux distribution. I just don't know. So, I think that's doable. I think single word audio recognition is doable. I don't think connected speech is doable by any amount of stuff we can have in the lab, because I think that's an artificial AI problem. Cranking up a big neural net on here would be interesting. Maybe not train it here, train it on in MATLAB, take the coefficients, take it over to the FPGA, use to solve some problem, real time. Maybe letter recognition. What are other ideas?
about like real-time auto-tune of the voice?
Oh, that would be interesting. Real-time auto-tune. Yeah, that's so there's a couple of interesting problems there. One is pitch determination. How do you get the pitch of a voice? And the problem here is that it's not a pure sine wave. If you're singing any vowel, you get a waveform that looks like this, where this is the fundamental, because the vocal cords are going open and slamming shut, and going open and slamming shut, and every one of those acts like an impulse that drives the linear filter, which is your throat. So you have, the model is you have a buzz generator down here, a long pipe, a mouth, a tongue, and lips, right? And you can model this as a resonator with about 10 sections. It's enough. 10 sections is enough. And what the tongue does is to change the cross-section of the resonator. When you move your throat, it changes the cross-sections down here. And the way you form these waveforms is by changing the structure of your throat. But there's also some hiss generated off the lips, some further back. So there's a couple of noise sources that have to be mixed in. And the result is this kind of damped impulse waveform that you have to decode to actually get the pitch. That is completely doable by cross-correlation or other mechanisms. There's a huge literature on pitch determination of voice. Once you do that, then you have to figure out how you're going to shift it a little bit. One possibility is a speech vocoder, which breaks speech down into dozens of bandpass filters, and then shifts the center frequencies of the bandpass filter slightly and resynthesizes it. And I know how to do that.
You do?
Yeah. The result is a little bit sing-song. I don't know if I played this for you or not. Let me see if I can find it pretty quick here. I think I'm going to have to show you a version running on the PIC32. How boring. So this is a voice sample.
1, 2, 3, 4, 5, 6, 7.
Okay, you get the picture. Now, this is through a 30-channel vocoder, but it's resynthesized not with the normal speech signal, but you take the input voice, you break it down into 30 channels. You get the average energy in each channel, averaged over 16 milliseconds. And then you use that energy as the amplitude for a sine wave at the center frequency of the filter. So what's coming out is 30 sine waves mixed together of the correct amplitude only.
1, 2, 3, 4, 5, 6, 7, 8, 9, 0.
So then you can ask what it sounds like with 15 channels.
1, 2, 3, 4, 5.
So it has kind of a robotic sound to it. Now we can shoot pitches. This is at 1.75 times higher. So there's other ways to do vocoders also. And one approach is to extract the pitch, extract and then do what's called linear predictive coding to get the shape of the throat. Once you've done the linear predictive coding and get the shape of the throat, then you change the excitation frequency by the appropriate amount, put that new buzz generator back through the same filter. And you'll get something that sounds a lot like the voice, but shifted up just a little bit. By the way, this is the original spectrum, and this is what it looks like after resynthesis, and yet they sound, I mean, the spectra are grossly different, and yet you can understand the speech. In fact, if you plot the maximum energy of the spectrum and use the sine waves at the maximum energy of the spectrum, you only need 5 sine waves to make understandable speech. Nobody actually knows why this works, but it works. So yeah, an auto-tuner I think has some challenges, but there's lots of interesting waypoints also, like just getting the pitch. What else? Head-related transfer function is really interesting to try. So you simulate the linear filtering that's due to your ears and shoulders and hair and make a sound. So my cell phone rings. I look over here. How do I know it's over here? It's through differential filtering between my 2 ears. If you know the filters that correspond to 90 degrees left, you could make a sound. You could take a sound, a monaural sound, and make it sound like it's coming from 90 degrees left, or above your head, or below you. So it would be fun to make a steerable sound source. Let's say you have an acoustic shooting game. You have a first-person acoustic shooter. You put on the earphones, you close your eyes, and you fire at where the sound is coming from. But you have to also be able to hear the projectile going away from you. Ooh, ah, that could be fun. That'd be cool. If you're into first-person shooters. There's algorithms like SLAM, single lens depth analysis. You shine a camera around an environment and it reconstructs a 3D image. That might be interesting to try and do on the FPGA. There's some, if you take any algorithm you can think of, SLAM, space FPGA, and search on Google, you'll find somebody that's done it. Voice pitch determination, FPGA. Right. Had one project one year. This was a Masters of Engineering project. When you closed your eyes to look away from the television, it turned off the television. It just turned off the liquid crystal display. You open your eyes, it's there. You turn back, it's there. You walk out of the room, it turns itself off. So it's got to be able to detect face and more or less whether your eyes are open. That's pretty interesting.
How did it work with blinking?
Yeah, there was some time constant involved.
Okay, so if you like close your eyes.
Yeah, it didn't do it right. So, another possibility, if you're into sort of renewables, is maximum power point controller for a solar array. Because you have to do dynamic impedance modulation of the load to get the maximum power out of a nonlinear, grossly nonlinear power source, like a solar panel. So you need a high-speed control system. The algorithms typically use up an ARM processor in modern inverters. So it's non-trivial. What else? Ooh, how about modeling the grid? Do a distributed model of generators and nonlinear loads that you could, and then use the HPS as you're the operator, right? You have to stabilize this system as a tree falls on the wire, the virtual wire. There was a PC game that had that format a few years ago. It was unbelievably hard to play because everything interacts with everything else. You know, there's three grids in the US. There's the Western grid, the Eastern grid, and Texas, of course. And so the Eastern grid is enormous. It's gigantic. It goes out to the Rocky Mountains. There's hundreds of generator sources. It's big enough that there's a phase shift across the grid. So what exactly is the power flow when you have a system that's big enough to have a distributed phase at 60 hertz? There's all kinds of control problems. How do you tell what's going on 1,000 miles away in real time when you're limited by the speed of light? It's interesting. What else? No self-driving cars. Maybe little cars, nothing you can ride in. Okay, then I'll be in lab this afternoon. Be happy to talk more. think about final projects. Over break, if you have any questions about final projects, shoot me an email. Otherwise, I'll see you next week in lab. And no lectures next week.